Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to bang out some practice problems related to thermodynamics, and I've chosen a pretty long list of problems, and some of them are multiple part problems, so I think this is going to be a pretty long live stream. And the problems that we're going to do are going to encompass all of the stuff pretty much that we've learned throughout volumes 1 through 6 of this thermodynamics live stream series. By the way, if you want to watch any of those episodes in my thermodynamics live stream series, look no further than the description below, where I've provided a link to a playlist called Thermodynamics Live Streams. It's got everything you need to know about the information that is required to solve the problems that we are about to do. So my goal for this stream is I would like it to be very interactive. I would like us to work on these problems together. So with that in mind, I hope you've brought your scientific calculator as we jump right into thermodynamics practice problems. As always, your feedback is more than welcome and highly appreciated. So please feel free to drop your thoughts in the chat if you're watching this live, or alternatively, you can call into the show using Discord. There's a link in the description for you to call into the show using Discord if you like. I think that would be a fun opportunity for me to chat with you voice to voice. Very few people take me up on that, but nonetheless, the option is there. And if you're watching this in the form of a video, please feel free to leave me a comment, because without your feedback, I am completely lost. All right, so I'm going to take you guys straight to the whiteboard where I've got the first thermodynamics problem lined up for you already. Let me sort of shift this around and resize it a little bit, make it nice and big. Okay. So this problem says to determine the sign of ΔSsys, that's the change in entropy of the system for each of the following processes. We have water boiling, water freezing, dew forming, and then we have this sort of diagram right here, which shows these two flasks that are connected to one another, and you have these 4 gas particles, and the change is going from a state in which the 4 gas particles are in the flask that's on the left-hand side to a state in which each flask contains 2 of the gas particles. So the important thing to remember here is that entropy is that thermodynamic property that is associated with disorder, with randomness, with energy dispersal. It's related to the number of places where energy can be placed within a sample of matter. So the idea is that the more random your sample gets over time, the more increase of an entropy you will have. Entropy will increase if you go from less random to more random, and entropy will decrease when you go from more random to less random. And so if you think about water boiling, right, this first one here, so what happens when water boils? Well, it goes from a liquid state, a state of matter in which the water molecules are fairly disorderly, to a gaseous state, to water vapor, in which the water molecules are even more disorderly. So if the amount of disorder or randomness increases, then that means that entropy, the entropy of this system, is going to increase, and therefore the sign of ΔS system for water boiling is going to be positive. So I'll put a little plus sign there. What about water freezing? Well, you imagine what happens when water freezes, right? You have a sample of liquid water, a fairly disorderly state, freezing into solid water or ice, which is a very orderly crystalline arrangement of those water molecules. And so since the degree of randomness decreases when water freezes, the entropy decreases, which means the sign of the change of entropy, ΔSsys, is going to be negative. Let's move right along to C. That's dew forming. So what is dew? Dew is condensation, right? You have these airborne water molecules, right? You have this water vapor that undergoes condensation it condenses into a liquid that we call dew, right? So you have water vapor, highly disorderly sample of water molecules condensing into a much more orderly sample of liquid water. And so if the randomness decreases, as it does when dew forms, the entropy will decrease. The sign of ΔSsys will be negative. And finally, this one here, this D, right? You have 4 gas particles on the left-hand side of the flask, and then at the end of this process, you have 2 gas particles in one flask and 2 gas particles in the other, right? So what happens to the entropy of this sample of 4 gas particles? Well, remember, entropy is related to the number of energetically equivalent configurations of a sample, right? And if you notice, right, we have these 4 gas particles over here. The only way that you can be in this state right here in the beginning is if all 4 of those gas particles are in that left-hand flask, right? There's only one energetically equivalent way to arrange the components of this sample, whereas the sample over here on the right, well, there's several possible ways, right? If you call the particles 1, 2, 3, and 4, you could have this arrangement where particles 1 and 2 are on the left and 3 and 4 are on the right. You could have a situation where 1 and 3 are on the left and 2 and 4 are on the right. And so there's much, much more energetically equivalent configurations of this situation over here, in which we have 2 particles in the left-hand flask and 2 particles in the right-hand flask. And therefore, the entropy of this is going to increase. And so therefore, this will carry a positive sign, right? ΔS will be positive. All right, so we're going to move right along to the next problem. So bear with me for just a moment while I go to the PowerPoint here and paste the next problem into the whiteboard. I really think that I need some kind of like elevator music or something while I'm doing these things, like while I'm moving from one problem to the next, just so there's not like this dead silence in between. But I guess it doesn't really matter that much because it doesn't take me too long to do it. So, okay, here's the next problem. So it's going to get a little bit hairier. All right. So it says the following. It says, without doing any calculations, determine the sign of ΔSsys and ΔSsurroundings for the following reactions. And it says to determine under what temperatures, high or low, the reaction is spontaneous. Right? So we're asked to determine the sign of ΔS for the system and the sign of ΔS for the surroundings, right? So it's important to understand that in thermodynamics, we always consider the universe as being composed of 2 components: the system, which in the event of a chemical reaction is simply the reactants and products of the chemical reaction, and then there's the surroundings, which is literally everything else in the universe. And so notice that both of these reactions are in the gas phase. All of the reactants and products in both of these chemical reactions are gases, right? And so if you want to know for a gas phase reaction whether the entropy of that system is going to increase or decrease, it's actually fairly simple. And the rule is that if you produce more moles of gas than you started with, in other words, if there are more moles of gas on the product side of the equation than there are on the reactant side of the equation, then the entropy of that system will increase. And then on the flip side, if you produce less moles of gas than you started with, in other words, the reactants have more moles of gas than the products do, in that sort of situation, entropy would decrease, the sign of ΔS would be negative. Now, it's important to understand that just because the entropy of the system is, let's say, positive, right? If the entropy of the system is positive, that does not necessarily mean that the reaction is spontaneous, because remember, the second law of thermodynamics tells us that for a spontaneous process, the entropy of the universe increases, not necessarily the entropy of the system, but the entropy of the universe, which is the sum of the entropy of the system and the entropy of the surroundings, right? So with that in mind, right, if we turn our attention to this first example over here, A, right? So we have the reaction that describes the combustion of propane, C3H8 plus 5O2 yields 3 CO2 and 4 H2O. And so the question is, does this reaction produce more moles of gas than you started with. So let's count the number of moles of gas. It looks like on the reactant side, we have 1 here and we have 5 over here for a total of 6, right? So 6 moles of gas in the reactants of this equation here. And if we look at the product side, we have 3 CO2s and 4 waters for a total of 7 moles of gas. And so for this problem, I'll just put this little a over here. We do indeed end up with more moles of gas than we started with. And so therefore, the sign of ΔS system, let me redo that, it looks like a lowercase s there. The sign of ΔS system is going to be positive, right? The entropy of this system increases because you produce more moles of gas than you started with. So then there's the question of the change in entropy of the surroundings. How do we figure out what the sign of the change in entropy of the surroundings will be? And in order to determine that, we need to understand the formula for how to calculate and how to quantify the change in entropy of the surroundings. And that is as follows, where we have the following. We have ΔS for the surroundings is equal to the negative of ΔH for the system divided by the temperature. So basically what this equation is telling us is that if you have an exothermic reaction, something with a negative value of ΔH, something that releases energy into the surroundings, that release in energy into the surroundings is going to increase the entropy of the surroundings, but it depends on temperature, right? If you release a given amount of energy into surroundings that are hot, it's not really going to have much of an effect upon the entropy of the surroundings. But if you release some energy into surroundings that are cold, that will have a profound effect upon the entropy of the surroundings. And so if we examine this formula here, right, we know that ΔS surroundings is equal to the negative of ΔH system over T. Now, the ΔH values for these reactions are shown, right? So the ΔH value of the value is not really super important, but the sign is very important, right? So the sign of ΔH for this reaction, this combustion of propane here, is negative. And so since ΔH for this reaction up here is negative, what sign do you think ΔS surroundings for this reaction is going to be? Well, it's going to be positive, right? Because if you take the negative of the ΔH, which is negative, well, a negative times a negative is a positive, right? So that means that the ΔS for the surroundings is positive, right? And the other formula that's really important to understand is that the change in entropy ΔS of the universe, UNIV, which remember, that's the criterion for spontaneity, right? Entropy of the universe increases for a spontaneous process, is equal to the sum of the entropy change of the system and the entropy change ΔS for the surroundings, right? And so we can see here that since the entropy change of the universe is the sum of the entropy changes of the system and the surroundings, and that the entropy changes of the system and surroundings are both positive, then the entropy change of the universe is going to be positive no matter what. No matter what the temperature is, this reaction will be spontaneous. The value of ΔS for the universe will be positive at all temperatures. So I'm going to keep these formulas over here, and we're going to move right along to B, right? So B. So let's start by determining the sign of ΔS for the system, right? ΔS for the system, will it be positive or negative? Well, it looks like in the reactant side of this equation, we have 2 + 1 or 3 moles of gas, but then on the product side, we only have 2 moles of gas. And so we can therefore conclude that the sign of ΔS for the system is going to be negative, right? The entropy of this system decreases. Now again, that doesn't necessarily mean that it's a non-spontaneous reaction, because again, the criterion for spontaneity is the entropy of the universe, right? So let's also look at the entropy of the surroundings, right? Well, we just established a moment ago that since the sign of delta H for that previous reaction was negative, that the sign of delta S for the surroundings must be positive, because when you multiply a negative times a negative, you get a positive. And that same principle applies in B, because the sign of delta H is also negative in the case of B, right? So we know, therefore, that the sign of delta S for the surroundings is going to be positive, right? And the magnitude of that value, the magnitude of the change in entropy of the surroundings, is going to be dependent on temperature. But notice that temperature is in the denominator, right? So the higher the temperature is, the smaller in magnitude the value of this delta S for the surroundings is going to be, right? So at high temperatures, this positive value becomes very, very small, and likely this negative value of delta S for the system is going to sort of outcompete or overcome that positive value, right? So at high temperatures, you're going to get a negative value of ΔSsys, which means you have a non-spontaneous reaction. So let me write that in this pink color here. So it's going to be non-spontaneous. I'll just say non-spawn, right? Non-spontaneous at high temperatures. And then also notice that since T is in the denominator of this formula, if that T is very, very low, then this overall expression becomes very, very high. You end up with a very, very large positive value of delta S for the surroundings, and therefore you're going to have a spontaneous reaction when the temperatures are low, right? So it's non-spontaneous at high temperatures, spontaneous at low temperatures. So it's just really all about understanding these formulas and how they work, and sort of what effect the sign of delta H has, and what effect the magnitude of the temperature, or the, how high or low the temperature is, what effect that has on the magnitude of your delta S for your surroundings. So, all right, that does it for that problem. So cue the elevator music again while I find the next one and paste it in here. Here we go. By the way, if anybody is watching this and you believe that this stream provides value to you, I would wholeheartedly appreciate your support in the form of a thumbs up on this video, because liking is sharing, right? When a video receives more likes, it gets promoted just a little teeny bit more in the algorithm. And if you look at my channel stats compared to what they used to be, well, let's just say I need all the help that I can get. So, all right. Begging speech is over. Let me go ahead, and I did not mean to rotate that. Okay, so let's go with this problem here. All right. Got a message from Ivan Fernandez. Says, have you ever been in a heated argument over Chem? Who got you mad? That's a good question. I don't think I ever got mad, but I remember my lab partner got mad at me. It was a pretty crazy story. So I was taking this physical chemistry laboratory, and the instructor of the lab was like really, really intense and very intimidating. You can kind of think of him as like the Gordon Ramsay of lab instructors. And before every experiment, you take an oral quiz where this guy just absolutely grills you and questions you on every little aspect of the experiment. And if you can't answer every question that this guy has adequately, then he deems you a safety risk, and you go home for the day and you get a 0 for that lab. So needless to say, a lot of pressure. And I had a lab partner that was assigned to me at random. We were assigned to each other at random for the entire semester. So it's like you got to cross your fingers and hope that you get a good one. And it wasn't looking good. We were taking our oral quiz on our first lab. We had already seen people get sent home, so we knew that the guy wasn't bluffing, and it wasn't looking good. I was trying to sort of talk my way out of getting a 0 on this lab, and she kind of blew up at me because she thought I was kind of leading us in the direction of getting sent home. But it turns out I was actually right. So, I mean, she apologized for that later, and I'm actually sort of still in touch with her to this day. Great person. She ended up being a great lab partner. But yeah, I don't know. I haven't really gotten any heated arguments over chemistry. It's mostly been it's been mostly peaceful interactions. All right, so let's get back to this problem. So this says that we have a reaction which has a delta H value of 130 kilojoules and a delta S value of 317 joules per Kelvin. And the question asks us, at what temperature is the change in entropy for the reaction equal to the change in entropy for the surroundings, right? So obviously the change in entropy of the reaction, that's given, right? 317 joules per Kelvin. So we're going to go back to that formula that we used before. It's too bad that I erased it earlier, but the formula is as follows, where we have delta S, the change in entropy of the surroundings, is equal to the negative of the delta H of the system divided by the temperature, right? And so at this point, it's just a matter of isolating T algebraically, right? And then plugging the numbers that we have in there and solving for it. And so algebraically, if we multiply both sides of this equation by T, we are going to get the following, where we have T delta S for the surroundings is equal to negative delta H for the system, right? And then finally, we're going to divide both sides of this equation by delta S of the surroundings, and we get that T is equal to negative delta H for the system divided by delta S for the surroundings. Now, it's important to notice that the units of delta H are kilojoules and the units of delta S are joules per Kelvin, right? And so in order to do this division problem here, in order to do this calculation, we need to be able to make sure that we have compatible units, right? So that means we either need to convert our delta H value into joules to be compatible with our delta S value, or we have to convert excuse me, or we have to convert our delta S value into kilojoules per Kelvin to be compatible with our delta H value. And I prefer to do the latter, right? So if our delta S value, right, delta S for this reaction is equal to 317 joules per Kelvin, right? I want to convert this into kilojoules. How do I do that? Well, I just set up a simple conversion factor. I'll put joules on the bottom and I'll put kilojoules on the top. Of course, there are 1,000 joules in 1 kilojoule, and my joules are going to cancel. My unit will be kilojoules per Kelvin. And so that's going to be 0.317 kilojoules per Kelvin, right? So now we have compatible units. Delta H is in kilojoules, delta S is in kilojoules per Kelvin. And so now we can plug these values into our formula here to solve the problem. So T is going to be the negative of delta H for the system. So delta H for the system given by the problem is 130 kilojoules, right? And then we divide that by the entropy change for the surroundings, right? So actually, hang on. Yeah, so we divide that by, sorry, I had a little bit of a brain meltdown there. Divide that by the change in entropy, again, because we're asking ourselves at what temperature does delta S for the surroundings equal delta S for the system. So they're going to have the same value. So that's 0.317 kilojoules per Kelvin, right? And make sure our units cancel. Kilojoules cancels with kilojoules. We're going to end up with kelvins, which is good because that's the unit of temperature. We're asked to figure out a temperature. So if you guys would like to follow along with your scientific calculator just to make sure I didn't mess up my calculation, I would wholeheartedly appreciate that. So bear with me while I perform this calculation. So we have minus 130 divided by 0.317. And the value that I got taken to 3 significant figures is, hey, that can't be right. That can't be right. Yeah, I messed up somewhere. I don't know where I messed up. Maybe I wrote the problem wrong and it should have been like negative 130 kilojoules. Yeah, something like that, because I end up getting a negative value, and I know that can't be right because it's impossible to have a negative temperature in kelvins. So, all right, so I don't have a good answer for this problem. By the way, I haven't solved any of these problems. I do try to proofread them, but apparently this one has slipped through the cracks. So yeah, this one, just understand this would be the methodology that you use to solve such a problem. Obviously, I got my initial values over here wrong. I really think this delta H should have been negative 130 instead of 130. That would have been that would actually make sense, because that would end up giving a positive value for temperature. But yeah. The way I'm calculating this, I'm ending up with a negative value for an absolute temperature, which is impossible. The lowest value on the Kelvin scale is simply 0 kelvins. So yeah, I don't really have a good answer for this one because I think I messed it up from the beginning when I wrote the problem. So I apologize for that, but the methodology is the important part of it. So let's delete all of this stuff and move on to the next problem. Sorry, guys. Let's continue and put that one in the rear view mirror, shall we? So cue the elevator music while I paste the next problem into this as we continue banging out some thermodynamics practice problems. Ivan says, I hate group work so much. Yeah, I mean, I don't know. There's advantages to it, and there's definitely some disadvantages to it, but I'm kind of with you. I like to just fly solo on most things. Which is why I operate my channel on my own. I don't work with anybody on my channel, which is why it's pretty stagnant lately, among other reasons. But all right, so moving right along to this problem here, the question is asking us to calculate the free energy change for the following reaction at 25 degrees Celsius. And the follow-up question is the reaction spontaneous? So the reaction is as follows, where we have 2 moles of calcium reacting with 1 mole of oxygen to give us 2 moles of calcium oxide. And notice that the standard change in enthalpy for the reaction and the standard change in entropy for the reaction are given, and they are minus 1,269.8 kilojoules and minus 364.6 joules per Kelvin, respectively, right? And so in order to solve this, we just need to have the formula for how to calculate delta G, change in Gibbs free energy, in our back pocket. And that formula is as follows, where we have delta G is equal to delta H minus T delta S, right? And this is usually how the formula is written, and it's written under the assumption that the reader knows that the values of delta H and delta S are defined with respect to the system, right? If you remember from when we talked about delta G way back when, the reason why delta G is such a useful thermodynamic property is because it is a criterion for spontaneity that can be calculated using properties that are only defined with respect to the system. That's a really advantageous position to be in as a chemist because, as you can imagine, measuring changes in enthalpy or entropy for the surroundings directly can be pretty difficult. So, but we don't have to, because we can just focus on the system, and we have this criterion for spontaneity here, right? So, okay, so all we have to do is simply plug our values into this. Just as in the previous problem, we need to make sure that our values of delta H and delta S are in compatible units, which right now they're not, right? So what I'm going to do is I'm going to take this delta S value, right? So this delta S value for the reaction, which is negative 364.6 joules per Kelvin. I'm going to do the same thing I did in the previous problem, and I'm going to set up a conversion factor in which I convert from joules to kilojoules, right? 1,000 joules in 1 kilojoule, right? My joules are going to cancel, and my new value of delta S is going to be in kilojoules per Kelvin, right? So minus 364.6 divided by 1,000, that's going to end up being minus 0.3646 kilojoules per Kelvin, right? So now that we have these compatible units between our ΔH and our ΔS, we can plug them into this formula here. So ΔG then is going to be the ΔH, right? ΔH, that's minus 1269.8 kilojoules, right? Minus the product of the temperature and the change in entropy. Now, it's also very, very important to remember that anytime you use a temperature in a thermodynamic formula, it must be an absolute temperature. And by that, I mean it must be in kelvins, right? How do you convert from degrees Celsius to Kelvin? Easy, just add 273 or 273.15. Really kind of all depends on, how many sig figs your degree Celsius temperature has, or how many decimal places rather. Notice that our value of temperature in degrees Celsius only goes out to the ones place. And so when I add 273 to it, I'm just going to add 273 to it. I'm not really going to worry about the 273.15. Right, so if I have 273 plus 25, that ends up being a temperature of 298 kelvins, right? So that's the temperature. And the value of ΔS, I'm just going to erase this just to give myself a little bit more room, is minus 0.3646, and that's kilojoules per Kelvin. Notice that our kelvins are going to cancel. We're going to end up with kilojoules over here, and so therefore our value of ΔG will have units of kilojoules as well. So I'm going to pull out my scientific calculator and solve this one once again, and I would encourage anybody watching this to do the same. So here we go. We have minus 1269.8 minus 298 times negative 0.3646. Now, what does that end up being? If we take this to, how many sig figs would that have? So I have 3, so we'll just do 3 sig figs here. So I'll put this in scientific notation so that we can keep it to 3 sig figs. So the question is, so the answer rather, is going to be minus 1.16 times 10 to the third, and that's kilojoules, right? And so we have our value of ΔG, right? We calculated it. We calculated our free energy change for this reaction. But the question is the reaction spontaneous? And the answer to that question is yes, it is, right? Because remember, for a reaction to be spontaneous, ΔG must carry a negative value. If ΔG carries a positive value, then you have a non-spontaneous reaction, right? So it's important to remember that relationship. All right, folks, so we're going to move right along. Cue the elevator music while I, as quickly as I can, paste the next problem into this software here. So give me a minute. Let's see. Okay, here we go. I'm going to enlarge it once again. All right. So this question asks us, for each pair of substances, choose the one that you expect to have a higher standard molar entropy at 25 degrees Celsius, and to explain the reasoning for your choice, right? So for each one of these, A, B, C, and D, we have 2 substances that are listed, and we want to be able to predict, based on what we understand about standard molar entropy, which one will have the higher standard molar entropy of the 2, right? So again, standard molar entropy, right? That's the amount of entropy, or the amount of energy that is dispersed in 1 mole of a substance, right? And those values of standard molar entropy that you would look up in a textbook are all values that are measured against the value of 0 for entropy. And there does exist an absolute value of 0 for entropy, which is defined by the 3rd law of thermodynamics, which tells us that the entropy of a perfect crystal at 0 kelvins is 0, right? So that's the zero value. So anytime you look up standard molar entropies, they're all measured against an absolute zero defined by the third law, right? So if we look at A, right, we have two substances, methane, CH4, and silane, SiH4, right? And so these two substances are very, very similar, right? They have a lot in common. They have a central atom, right? And if you look at your periodic table, you'll find that carbon and silicon are in the same group, the same vertical column of the periodic table. So they have similar chemical reactivity, which makes sense why they would both bond to 4 hydrogen atoms, right? So they have similar chemical reactivity, very, very similar substances. The only difference is that in the place of carbon, we have a silicon atom, right? And so what can we apply about what we know about standard molar entropies, relative standard molar entropies? Well, we know, right, since silicon lies below carbon on the periodic table, that silicon has a larger molar mass than carbon does. And so therefore silane, SiH4, has a larger molar mass than methane does, right? And another thing that we went over when we were talking about the various factors that affect standard molar entropy is that standard molar entropy tends to increase with increasing molar mass if all other things are equal. So in general, if all other things are controlled for, the higher your molar mass, the higher your standard molar entropy. Since silane has a higher molar mass than methane, and these two molecules are very, very similar otherwise, it is silane, SiH4, that is going to have the higher value of standard molar entropy. So there's that one. If we move right along to B, right, we have two substances, right? We have this thing here, CH3, CH2, CH2, CH3. That's like a structural formula for a compound called butane. You might be familiar with it, right? Like any cigarette lighter, and it's butane gas that's burning in that lighter, right? So we have butane, and then we have sulfur dioxide. Now, if you look up the molar masses of butane and of sulfur dioxide, you'll find that they're actually pretty similar, right? So if you pull out your periodic table and you add together the individual molar masses of every atom in these two compounds, you'll find that they're very, very similar. They're very, very comparable in terms of molar mass. So we can't really use molar mass to determine necessarily which one of these is going to have the higher standard molar entropy. But one thing that's jumping out at me is that this butane here is a much more complex molecule, right? Sulfur dioxide is just a sulfur with 2 oxygen atoms bonded to it. It just has those 2 bonds from sulfur to oxygen. Meanwhile, butane here has a bunch of bonds, right? You have these 4 carbon atoms that are bonded together, right? So there's 3 bonds right there. And then each of those carbons has either 3 or 2 hydrogens on it. So there's way more bonds, right? And with way more bonds comes way more complexity. With way more complexity comes way more places where energy can be put, right? Because those bonds, they can wag around, they can rotate, they can vibrate. So all of those vibrations and rotations and this and that, those all represent additional places in which energy can be dispersed, right? And so since the complexity of the molecule in the case of butane is so much higher than that of sulfur dioxide, it is butane that we would expect to have a higher standard molar entropy at 25 degrees Celsius, right? So moving right along, we're going to tackle this C now. So we have CH3OH, that's methanol, right? So we have liquid methanol, and then we have gaseous methanol, right? So it's the same substance, it's just one's a liquid and one is a gas. And this one I think should be pretty straightforward, right? Because we understand that entropy is a measure of randomness or disorder. We also understand that gases are more random than liquids, which are more random than solids, right? And so therefore we would expect gaseous methanol to have the higher standard molar entropy because, again, gases are more random. They have more entropy than liquids than solids, right? So that one is kind of a no-brainer. And then finally, if we look at D, we have potassium bromide, solid potassium bromide over here on the left, and then we have aqueous potassium bromide that has been dissolved to make an aqueous solution over here on the right. And again, this is a pretty straightforward concept with standard molar entropy. In general, things that are dissolved to form a solution have higher standard molar entropy values than their undissolved or solid counterparts. That's usually the case. There might be some rare exceptions, but usually things that are in solution have higher values of entropy than things that are not in solution. So there we go. There's the standard molar entropy, relative standard molar entropy problem. So we're going to move right along and paste the next problem in here. By the way, like I said before, if you guys find this stream valuable, please do me a favor and leave a thumbs up on it, because liking is sharing. And also, if you wanted to take it a step further and support the stream monetarily, that would be very welcome as well. There's a couple of different ways to do that. You can donate via super chat, very, very easy, although YouTube does take a pretty significant cut of super chats. The other way that's a little more difficult, but the service takes less of a cut, is to donate through Streamlabs. There's a link down below in the description under the heading Support the Stream, which you can donate through PayPal using Streamlabs. I think you can even do like text-to-speech donations and fun stuff like that. So again, any kind of support from you guys, even just an attaboy, would be welcome. Yeah. All right. So let's do this problem here. So this problem says to consider the following reaction, where we have 2 moles of nitric oxide, NO, reacting with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide, NO2. And we are tasked with estimating the standard change in free energy for this reaction at 750 kelvins. And it also says to assume that the standard change in enthalpy and the standard change in entropy do not change much within the given temperature range, right? So this problem is going to get pretty lengthy. I'll just go ahead and warn everybody right now. This is going to be a pretty long problem. So let's sort of start with the end and then sort of work backwards in terms of the formula. So the formula that we're ultimately going to use to solve this problem is the following, where we have delta G for the reaction. Excuse me. We have delta G for the reaction under standard conditions is going to be equal to the standard change in enthalpy of the reaction, delta H, minus T delta S. And of course, delta S is going to be under standard conditions as well, right? So this is the value that we are going to use. Now, normally, if I'm trying to calculate the standard change in free energy for a reaction, what I would normally do is to take the easiest approach, which is to use tabulated standard free energies of formation. But we can't really do that here because tabulated standard free energies of formation only apply at the temperature range for which they're tabulated, which is usually 25 degrees Celsius, but we're asked to estimate this at 750 kelvins, right? Which is definitely not standard conditions, right? So basically, what we need to do, right, is we need to determine the values of delta H for this reaction and delta S for this reaction, and we're going to do that using tabulated standard free energy, or tabulated standard enthalpies of formation, and we're also going to use tabulated standard molar entropies. Again, these things are tabulated. They can be found in the appendix of your chemistry textbook. I promise they're back there somewhere. And then once we figure out what the standard values of the entropy and the enthalpy change are, then we can plug those into this formula here, and that'll get us our desired value of delta G, right? So let me see if I can move this as far upward as I can, because I'm going to need a whole lot of room here, right? A whole lot of room. So the first thing we need to do is we need to hit the books, and we need to look up the appendix of our chemistry textbook. We need to look up the tables to find the values of delta H of formation and the standard molar entropy for every reactant and every product within this chemical equation. So over here on the right hand side, I'm basically going to construct a little table here, right? So what we're going to have is the following, where we're going to have the entropy values, right? The standard molar entropy. Try to leave myself enough room here. And that's usually reported in joules per Kelvin, right? And then we're also going to have the standard enthalpy of formation, delta H of formation, and that's usually reported in kilojoules, right? We'll say joules per mole per Kelvin. That's usually how it is because it's standard molar entropy. And the standard enthalpies of formation are going to be kilojoules per mole. And I just realized that I'm off the page here, so let me actually, instead of that, let me just see if I can scroll down and just sort of resize this a little bit. Yeah, I think that's what I want to do there. Okay, so we have, basically this is like a row of the table, right? And then in our columns, we'll have each of these substances, right? So we have nitric oxide. Let's switch back to the pen here. So we have nitric oxide, which is a gas. We have oxygen, O2, which is a gas. And we have nitrogen dioxide, which is also a gas. And so at this point, our task is to look up these values in the table, jot them down into this table here, and then we can plug them into the formulas to find delta H and delta S for the reaction, right? So I've already done this ahead of time. I'm trying to be nice and tight and prepared for my live stream, right? I don't want to have to flip through my chemistry book on live on stream. So I've already looked these up. So if we're looking at the standard molar entropies for all these things, in the case of nitric oxide, it's 210.8 joules per mole per Kelvin. For oxygen, it's 205.2. In the case of nitrogen dioxide, it's 240.1 joules per mole per Kelvin. So that takes care of standard molar entropy. And then for standard enthalpies of formation, for nitric oxide, it's 91.3 kilojoules per mole. Then we have 0 in the case of oxygen. And then we have 33.2, and that's kilojoules per mole in the case of nitrogen dioxide. So we have jotted down our tabulated standard molar entropies and our standard entropy or enthalpies of formation for all of our reactants and all of our products in the equation, right? So now we're in a position where we can calculate delta H and delta S under standard conditions for this reaction. Can't shake this cough that I have, you guys. Sorry. All right, so let's start with, I'll do this, I'll just do it in black. Let's start with delta H for the reaction, right? So the formula to calculate delta H for the reaction is very, very similar for calculating the change in entropy for the reaction, or furthermore, the change in Gibbs free energy for the reaction. It's basically the sum of the enthalpies of formation, standard enthalpies of formation of all of our products multiplied by their stoichiometric coefficients minus the sum of the standard enthalpies of formation for the reactants multiplied by their stoichiometric coefficients, right? And so if we look at the products, that's going to be the coefficient in front of our only product here is 2. So that's 2 times standard enthalpy of formation of NO2. So that's 33.2. And that's kilojoules per mole, right? And we're going to subtract from that the same thing for the reactants. So we're going to have 2 times, because the coefficient in front of that NO is 2, times the standard heat of formation of nitric oxide, which is 91.3 kilojoules per mole, right? And we're going to add to that the standard enthalpy of formation of oxygen, which is actually 0, so we don't have to really worry about that. So let me grab this and sort of move it over here to make it nice and tidy here. So really it's this expression right here, 2 times 33.2 minus the quantity of 2 times 91.3, right? And that's going to give us our delta H for this reaction. So bear with me while I plug this into my scientific calculator, and I would encourage anybody following to do the same thing. So here we go. Yeah, I think I'm going to do that in future streams where I'm just going to like click on something that just plays like this elevator music while I'm banging out a calculation, just so there's not a bunch of dead silence. So here we go. So we have 2 times 33.2 minus the quantity of 2 times 91.3. 91.3. Okay, and the value that I got is minus 116.2, and that's kilojoules per mole. Minus 116.2 kilojoules per mole. So for those of you who are joining us late, basically we're using this formula in purple over here, delta G is equal to delta H minus T delta S, to estimate the free energy change for this reaction taking place at 750 kelvins. In order to do that, we need to use this formula here, but in order to use this formula, we need to calculate the values of delta H and delta S for this reaction using tabulated standard enthalpies of formation for in the case of delta H, and tabulated standard molar entropies in the case of delta S. And where we are at right now is that delta H calculation, which we just performed here. So what I'm going to do is I'm going to sort of delete all that calculation mumbo jumbo, and I'm basically going to take our value of delta H that we worked so hard to calculate, and I'll put it, I guess I'll put it over here, right? We're going to save that for later. So now that we have delta H, we can do the same thing with delta S, right? So delta S for this reaction is going to be the sum of the standard molar entropies of the products multiplied by their coefficients minus the sum of the standard molar entropies of the reactants multiplied by their coefficients, right? And so our product is NO2, so the coefficient in front of NO2 is 2, so it's going to be 2 times standard molar entropy of NO2, which is 240.1, and that's joules per mole per Kelvin, right? So that's the products, and we're going to subtract from that a very, very large term, right? So our first reactant, that's nitric oxide, NO, coefficient in front of that is 2, so it's going to be 2 times standard molar entropy of NO, that's 210.8 joules per mole per Kelvin, according to our table. And we're going to add to that the standard molar entropy of oxygen multiplied by its coefficient. Of course, its coefficient is 1, so we can ignore that. And that value is 205.2, and that's joules per mole per Kelvin, right? So this whole entire expression here is going to be subtracted from this expression up here, this 2 times 240.1, right? So again, cue the elevator music and bear with me while I do this calculation. So we're going to end up with delta S for this reaction is equal to something. I just haven't calculated it yet. And again, I'm doing all these problems for the first time. I haven't solved them beforehand, so I don't have like the answer in front of me. Kind of reminds me of like those cooking shows, you know, where like they show you like how to prepare a turkey. They put it in the oven, but then next to that, they already have an oven with like, that's like perfectly timed, and they have like the turkey like ready to come out of the oven. Yeah, I'm not that prepared for my live stream. What can I say? I got 2 small children. Anyway, I'm going to perform this calculation now. So, okay. So we have 2 times 240.1 minus the quantity of 2 times 210.8 plus 205.2. And the value that I got for the delta S standard of this reaction is minus 146.6 joules per mole per Kelvin, right? And because I've done many problems like these before, I immediately notice that we are going to run into a problem where we, like we have in the previous examples, where we need to make sure that our units for our entropy and our enthalpy change are compatible. One is in joules per mole per Kelvin, the other is in kilojoules per mole. So basically, I'm just going to do the quick joules to kilojoules conversion for this ΔS value, and we're going to get a value of negative 0.1466, and that's kilojoules per mole per Kelvin. So really all I did here was take this minus 146.6, divide it by 1000 in order to convert it to kilojoules. So I just kind of did that in my head really quickly, which I don't recommend, but I'm doing it just to speed things up for this live stream here. So I'm going to sort of erase all this calculation stuff that I no longer need, just to keep things nice and clean and tidy here. So I'm going to delete that. I'm going to drag this stuff over here, bring it closer to my ΔS symbol over here. I'm going to drag this entire thing, move it over there. And now that we have successfully calculated our enthalpy and entropy changes for this reaction, we no longer need this table here. So I'll go ahead and toss this table as well, just to make sure we have enough room to carry out our calculation here. Okay, so now that we have all of the values that we need in this formula over here in purple, we can finally apply this formula to get us the free energy change, or the estimate of the free energy change that we desire, that we want, that the problem asks us to get. So let me drag these two. Oh boy, it's not wanting to cooperate with me. There's like a perfect like interval of time that you have to wait in order to drag something that you select. There we go. It looks like I got it on that one. Okay, so I did not mean to do that. Let me fix that. Still trying to get the hang of this software here. Okay, looks like I got it where I want it now. All right, so I'm going to switch back to this purple pen, and we can finally use this formula, as I just mentioned. So the ΔG is going to be equal to the ΔH for the reaction, which is minus 116.2 kilojoules per mole, minus the product of the temperature and the ΔS. Now the temperature, that's given by the problem, that's 750 kelvins, right? And then the other term that we're going to multiply that temperature by is the ΔS value, which is minus 0.1466, and that's kilojoules per mole per Kelvin. Our Kelvin terms are going to cancel out. We're going to end up with kilojoules per mole. So what I'm going to do, since I have a scientific calculator, it's a very, very nice scientific calculator too, not expensive, but very, very nice and provides a lot of utility. I can enter this entire expression into my calculator. I don't have to like do that multiplication of 750 and 0.1466 first, write that down, and then do the subtraction. I can do the whole expression within this calculator. This is the TI-30X2S. I think it runs for about like $30. I should really do some affiliate marketing so I could like get a commission off of selling these things, but I don't. I'm not paid to promote anything with regard to calculators. This is just something that I use and that I recommend. And this is old too. Like I used this back when I was in college, and that was a long time ago. So, all right, bear with me while I get this value figured out. So it's minus 116.2 minus the quantity of 750 times negative 0.1466. I guess we'll just take it to one decimal place. So what I ended up getting was minus 6.25, right? If I were to round that, I would probably round it down to the 2 because it's even. There's a lot of dispute about rounding when you're exactly halfway in between digits. Some people tell you to always round up when the next digit is a 5, but the way I learned it from a professor that I really, really respect is that you round to the even digit. So if the even digit is the upper one, then you round up. If the even digit is the lower one, then you round down. So the number that I would get would be, it looks like I'm off the page again. I don't know what is going on, why my cursor keeps doing that. but let's just ignore decimal places and sig figs. My calculator spit out 6.25 or minus 6.25. And of course, the unit is kilojoules per mole. And so based on this estimate, would we expect this reaction to be spontaneous at 750 Kelvin? Yes, we would. Why? Because delta G has a negative value. Delta G is negative. That means your reaction is spontaneous. So there we go. All right, everybody. So we are moving right along. I think I might have skipped a problem by mistake. Yeah, I skipped a problem, but we kind of already did a similar problem. So I think I'm just going to omit that from the stream at this point. I don't think there's any practical reason to do the problem that I accidentally skipped. So yeah, we're going to move on. We are going to move on. So I just copied everything. Let's see. All right, this one, I always dread problems like these because they're so long-winded and it's really hard to manage my whiteboard space so that I'm not super cluttered all over the place. Everybody tuning out. All right, so this problem says to consider the following two reactions. So we have two reactions listed here. One of them is where you have 2 moles of iron reacting with 3/2 of a mole of oxygen to produce iron 3 oxide, or ferric oxide, Fe2O3. Right, so that's the first reaction, and it gives us the delta G, the standard delta G value for this reaction, which is minus 742.2 kilojoules. And then the next reaction is where you have carbon monoxide reacting with 1/2 of a mole of oxygen to produce 1 mole of carbon dioxide, and that has a delta G value of minus 257.2 kilojoules. And it says to use this information to find the standard Gibbs free energy change for the reaction below. And the reaction below is iron oxide reacting with 3 moles of carbon monoxide to produce 2 moles of iron and 3 moles of carbon dioxide, right? So what the heck is going on here? Well, what this has to do with is the idea of the relationships involving delta G for a reaction, right? So delta G, just like delta H, is a state function, and you may remember from back when you were studying thermochemistry about that Hess's law thing, right? Hess's law tells us that if a reaction can be expressed as the sum of a series of reactions, then the delta H for that summation reaction is the sum of the delta H values for the individual steps that make up that overall reaction. And the same principle applies to free energy. The same principle and logic applies to delta G, right? So if a reaction can be expressed as the sum of a series of reactions, then the delta G for the overall reaction is the sum of the delta Gs for the individual reactions. Now, so basically what we need to do here is we need to manipulate these two equations through some combination of either reversing one or more of the equations or multiplying one or more of the equations by a factor, right? We need to manipulate these equations such that when they are added together, they give us the overall, what I like to call, target equation that is listed down here, right? So I think what I'm going to do, and again, there's really no easy way to do this, but I think what I'm going to do is I'm just going to copy these two equations over here and what their delta G values are so that we can sort of manipulate our equations and make sure we are manipulating the value of delta G accordingly along with our manipulations of this equation. So here we go. So let me go ahead and copy everything. So we have the first one over here. This is, make sure I'm on the page here. Okay. I don't know what's going on. I keep getting this like pop-up window thing. It's really annoying. Okay. So we have 2 Fe, and I'm just going to omit the states of matter just to speed things up. So we have 2 iron plus 3/2 of an oxygen yields Fe2O3, right? And the delta G for that is equal to minus 742.2 kilojoules, right? So that's our first equation. Second one is we have carbon monoxide plus 1/2 of an oxygen, giving us CO2. And that delta G is equal to minus 257.2 kilojoules, right? Okay, so again, the idea is we need to manipulate these equations such that when they are added together, they will give us this equation up here. Notice that if we add these two equations together as they currently are, they are not going to give us the equation that we want. So we definitely need to manipulate them. And so it's kind of like solving a puzzle, right? So one thing that's sort of jumping out at me is that our target equation has 2 iron in the products in the right-hand side, but our only equation here that has iron has the iron on the reactant side. So let's first try to flip this equation. Let's reverse this equation to see if that gets us any closer to solving the problem, right? So if we flip the equation, what is it going to look like? Well, we're going to have the Fe2O3 is now going to be on the left-hand side of the equation, and then the 2Fe and the 3/2 O2 are now going to be on the right-hand side of the equation. And so the question then becomes, well, if we reverse a chemical equation, what do we have to do to delta G, right? How does the reversal of the equation, how is that reflected in the Gibbs free energy change of the reaction? And the answer is that if you reverse an equation, then delta G changes its sign. And so negative 742.2 kilojoules becomes positive 742.2 kilojoules when we reverse this equation, right? So another thing that's sort of jumping out at me is that our target equation has 3 moles of carbon monoxide, right? But the only equation that has carbon monoxide is this second one, and it only has 1 mole. And so what if we take this entire equation and we multiply it by a factor of 3, right? So we're going to take this entire, excuse me, this entire equation right here, and we're going to multiply it by a factor of 3. So what is that going to do? Well, that's going to change the coefficient of every reactant and product in this equation. So 1 mole of CO becomes 3 moles. 1/2 of a mole of oxygen becomes 3/2 of a mole of oxygen. And then 1 mole of CO2 becomes 3 moles of CO2, right? So we just multiplied this equation by a factor of 3, and we have taken care of our coefficients accordingly. But one thing we definitely need to make sure that we also take care of is our delta G. And the rule for multiplying equations by a factor is that if you multiply a chemical equation by a factor, you multiply the delta G value by the same factor, right? So this minus 257.2, we're going to multiply that by 3 since we've multiplied our equation by 3, right? So bear with me while I do this into my calculator. Again, I would highly encourage anybody following along to do the same. Grab your calculator, do the same calculations, make sure one of us doesn't make a mistake. It's entirely possible that I make a mistake. So we have minus 257.2 times 3. That is equal to minus 771.6 kilojoules, right? Okay, so I think we are cooking with gas now. I think we are getting somewhere. So if I add these two equations together, does the sum of these two equations equate to this equation up here? Well, let's take a look at it, right? So we have Fe2O3. Okay, so we have Fe2O3 over here on the left side of this equation. We have 3 carbon monoxide. Oh, yep, look, we have 3 carbon monoxide over here on the left. We have 2 iron on the right. Yep, we have 2 iron on the right, shown over here. 3 CO2. Oh, yeah, look at that. We have 3 CO2 over here. Now we do have those 3/2 oxygens, but notice that the 3/2 oxygen on the right-hand side of the first equation cancels with the 3/2 oxygen over here on the left-hand side of the second equation, right? So it does indeed look like if we add these two equations together, we get the target equation. And finally, all we have to do now to get the delta G of our summation equation is to simply add together the delta G's of our two manipulated equations, and that'll get us where we want to be. So again, bear with me while I perform this calculation. So we have 742.2 kilojoules minus 771.6 kilojoules. And the value that I got was minus 29.4 kilojoules, right? So that's how you do that. And this reaction is apparently spontaneous under these conditions. Why? Because, you know, delta G has got a negative value. All right. I want to know kind of where we are, everybody. The chat has been eerily quiet, so I would like people to sort of speak up. Let me know what you think of how this has been so far. Has it been good? Has it been insightful? Has it been valuable? Or has it just been one big waste of time? I mean, I can handle the truth, but I want to know what it is. So, all right, so let's delete all this stuff and move on to the next problem. I'm going to grab it, paste it, cue the elevator music. I think this is, we're sort of coming close to the end here. I think we have 2 more problems to go. So for those of you who have been watching, thank you for watching. And as I said just a moment ago, I would appreciate your feedback. I can handle even the harshest of criticisms, believe me. So be creative in your feedback. I want to read it. All right. Okay. So here's the problem. So the problem says to consider the following reaction where we have methanol, gaseous methanol, CH3OH, reacting to form carbon monoxide and 2 moles of hydrogen gas. Notice that this is a reversible reaction. It's an equilibrium reaction as indicated by these 2 opposing half-headed arrows, right? And of course, equilibrium, that just means the condition at which the rate of the forward reaction is equal to the rate of the reverse reaction. So that's all that equilibrium means. And it says to calculate delta G for this reaction at 25 degrees under the following conditions, where we have a partial pressure of methanol of 0.855 atmospheres, a partial pressure of carbon monoxide of 0.125 atmospheres, and a partial pressure of hydrogen at 0.183 atmospheres, right? So it's important to know what formula we are going to use to calculate this. So this has to do with calculating delta G under non-standard conditions. Notice that this delta G symbol over here, it doesn't have that little degree sign superscript up there. That's what indicates standard conditions. This is delta G under non-standard conditions. And so we need to know the formula that we're going to use to calculate delta G under non-standard conditions. And that formula is as follows, where we have delta G for the reaction. That looks more like a 6 with a tail or something. Let me clean up that G a little bit. So delta G for the reaction is going to be equal to the standard delta G for the reaction plus RT times the natural log of Q, where Q is the reaction quotient, right? And the reaction quotient, that carries the same expression as the equilibrium constant. It's going to be the partial pressures of the products raised to the power of their coefficients divided by the partial pressures of the reactants raised to the value or to the power of their coefficients, right? And so let's start it off by, well, I mean, there's a lot to this problem, right? Because not only do we have to figure out the reaction quotient, but we also have to figure out what the standard change in Gibbs free energy of this reaction is, right? So let's start by finding out what the standard change in free energy for this reaction is. In order to do that, we're going to have to use tabulated standard Gibbs free energies of formation. So what I'm going to do is I'm going to make a little table over here on the right. So I'm going to have delta G of formation standard, right? And that's usually reported in kilojoules per mole, right? And I'm going to list off all of my reactants and products here. So we have methanol, CH3OH, which is a gas. We have carbon monoxide, which is a gas. And we have hydrogen, which is also a gas. So let's look up our tabulated standard free energies of formation. Again, you can find these. There's an appendix in the back of your textbook, and in that appendix is a table, and in that table you can find these values, right? So I've already written them down ahead of time in an effort to be prepared. So for methanol, what is it? It's minus 162.3 kilojoules per mole. For carbon monoxide, it's minus 137.2 kilojoules per mole. And again, I would encourage anybody to look these up yourself, because maybe I looked them up wrong. Maybe I was like reading the wrong row in the table or something. I don't know. It's entirely possible. And then for hydrogen, it's 0 kilojoules per mole, right? Because the standard free energy of formation of a pure element in its standard state is 0 by definition, right? So, all right. So now that we have our tabulated standard free energies of formation, we can use them to calculate our standard delta G for this reaction. And so how do we do that? Well, pretty straightforward, right? It's just the sum of the free energies of formation of the products minus multiplied by their coefficients minus the sum of the free energies of formation of the reactants multiplied by their coefficients. So what is that going to look like? So we're going to have our delta G standard for the reaction is going to be equal to, if we start with our carbon monoxide, the coefficient in front of that CO is 1, so we can ignore that. The standard free energy of formation of that CO is minus 137.2 kilojoules per mole. And that's going to be plus the standard free energy of formation of the hydrogen multiplied by its coefficient. So its coefficient is 2, and that's going to be times 0. So that pretty much negates this entire term here. So we've got our standard free energies of formation of the products, and then we are going to subtract from that the free energies of the reactants multiplied by their coefficients. So that's going to be the coefficient in front of that methanol is 1, so we can ignore that. So it's going to be minus negative 162.3 kilojoules per mole, right? So delta G standard for this reaction is going to be equal to this expression, minus 137.2 minus negative 162.3 kilojoules per mole. Bear with me while I figure this out. Again, I would encourage all you guys to do the same. So here we go. Minus 137.2 minus the negative, so plus 162.3. And I got a value of positive 25.1 kilojoules per mole. Positive 25.1 kilojoules per mole. So that tells us that under standard conditions, this reaction is non-spontaneous because delta G has a positive value, right? So, okay, we've used this calculation, so we don't need that anymore. We've used everything in this table. We no longer need this table. So what I'm going to do is I'm just going to take this delta G value. Looks like I accidentally cut off my kilojoule unit over there. So let's fix that. So kilojoules per mole. All right. So we have delta G. R, that's a constant that we should commit to memory. We'll plug that in later. T, that's the temperature, that's given. That's an easy conversion from degrees Celsius to Kelvin. We can handle that later. Q, on the other hand, that's the reaction quotient. That's the equilibrium concept. So all the stuff that we learned from chemical equilibrium is coming back. It's bubbling to the surface, so to speak. So, chemical equilibrium, it's not something that you can just learn about and then toss aside, never to use again. Nope, it comes back over and over and over again in chemistry. So it's important to have a solid understanding of it. If you don't, fear not, because I do have a playlist called Chemical Equilibrium Live Streams. If you're interested in it, I can direct you to it. All right, so Q. Let's calculate Q. That's the reaction quotient, right? So that's going to be equal to the partial pressure of carbon monoxide raised to its coefficient, which is 1, times the partial pressure of hydrogen raised to its coefficient. So we're going to square it. And we're going to divide that expression by the partial pressure of methanol, CH3OH, raised to the power of its coefficient, which is 1, right? So we're going to just plug in all of these values here. So we're going to have 0.125, that's the carbon monoxide, times hydrogen, that's 0.183. That's going to be squared. And we're going to divide that whole thing by 0.855, the partial pressure of the methanol. So bear with me while I calculate this. So we have, let's see, 0.125 times 0.183 squared. And we're going to divide that by 0.855. And the value that I got is equal to, I'm worried, I'm concerned. Should I put this in scientific notation or shouldn't I? Yeah, I'll go ahead and leave it out of scientific notation. I got a value of well, why is that green? It should be blue. 0.00, here, let me try that again. 0.00490, and that is unitless. That's just a number, right? Reaction quotient does not have any units. Okay, so we got that value, so I can erase all this calculation mumbo jumbo that sort of led up to it. So let's see. I'll go ahead and erase that. I'll take this over here. I'll just kind of drag it over here. Okay, so the two hard parts are done, right? We calculated the standard free energy change for the reaction. We calculated the reaction quotient. And so now we just have to plug them into this formula and we will be all set, right? Yes, we will. All right, so let me go back to this purple pen here. So delta G for this reaction is going to be equal to the standard delta G. That's positive 25.1 kilojoules per mole plus RT ln of Q, right? So R, what is that? That's 8.314 joules per mole per Kelvin, right? Now, one thing that's really jumping out at me is that R is in joules per mole per Kelvin, but our delta G is in kilojoules per mole. That's a problem. We need to convert one of these or the other, right? I'm going to go ahead and convert my R into kilojoules per mole per Kelvin, right? And to do that, it's just a simple conversion from joules to kilojoules. There are 1,000 joules in a kilojoule. So if we're going from joules to kilojoules, we're going to divide by 1,000. So 8.314 divided by 1,000. Just put this in my calculator just to make sure I'm doing it right. So that's going to be, I'll just erase that. So that's going to be 0.008314, and that's kilojoules per mole per Kelvin, right? So that whole R is equal to 8.314 joules per mole per Kelvin. That is something that is just really, really important, really useful to commit to memory. So I would highly recommend that you do that. And so then we have the temperature, right? So the temperature says it's 25 degrees Celsius, but not so fast. We got to convert that to kelvins if we want it to be useful in a thermodynamic equation. So that's going to be 25 degrees Celsius. We're going to add 273 to that to get the Kelvin temperature. So that's 298 kelvins, right? And looks like I'm running off the page here. So let me zoom out just a little bit. Okay. And then, so we have the, finally, we have the natural logarithm of the reaction quotient. So it's going to be the natural log of Q. So that Q is 0.00490, right? So this whole expression here is, once we calculate that, then we'll have our value of delta G for this reaction, right? So again, I really like this scientific calculator because I can just plug this whole, I can just type this whole expression in and just press a button and it'll just spit out the answer for me. So I'm going to go ahead and do that. So we have 25.1 plus the quantity of 0.008314 times 298 times the natural log of 0.0049. And the value that I got for the delta G for this reaction is positive 11.9. Positive 11.9. So just to recap all the steps that we took, so we understood the formula, right? Delta G for the reaction under non-standard conditions is equal to our standard delta G plus RT ln Q. We calculated our standard delta G using tabulated standard free energies of formation, right? The sum of the free energies of formation of the products multiplied by their coefficients minus the sum of the free energies of formation of the reactants multiplied by their coefficients. And then sort of sideways to that, we calculated Q, right? The partial pressures of the products raised to the power of their coefficients divided by the partial pressures of the reactants raised to their coefficients. And then we sort of put it all together in this formula here to get our value of delta G under non-standard conditions. All right, everybody. So we have one more problem to go before we wrap things up for the night and I send you guys on your way. Not like I'm actually sending you on your way. You're free to leave, and many people have. People just hop in here and decide it's not for them and then go. That happens a lot. I need to figure out how to keep people in here. But anyway, I'm going to go ahead and paste the last problem of the night in here, and then we will be finished. All done with thermodynamics. So, all right. So, here we go. All right. Okay. So, our last problem of the night asks us to calculate the equilibrium constant for the following reaction at 25 degrees Celsius. So the reaction is as follows, where we have 2 moles of hydrogen sulfide gas reacting at equilibrium to form 2 moles of hydrogen gas and 1 mole of diatomic sulfur, right? So the formula that we're going to use is as follows, where we have delta G standard for the reaction is equal to negative RT times the natural logarithm of K. So this is a good formula for the equilibrium constant. Now you can derive this formula if you know the formula for delta G under non-standard conditions, but I think this formula is pretty good to have memorized as well. So delta G is equal to negative RT times the natural logarithm of K, right? And so algebraically, what we need to do is we need to solve for K. We also need to figure out what the standard free energy change for this reaction is. So that's pretty easy. We're just going to use those tabulated standard free energies of formation. So I'll go ahead and just make my table over here on the right, where I have the delta G of formation standard, right? And that's in kilojoules per mole, right? Let me drag my board over here for a second. So we have standard delta G, kilojoules per mole. We have 3 substances. We have hydrogen sulfide gas, right? We have our hydrogen gas, and we have our diatomic sulfur gas, right? So again, these can be found in the appendix of your chemistry textbook, but I have already written them down ahead of time, so allow me to populate this table now. So with hydrogen sulfide, it's minus 33.4 kilojoules per mole. For hydrogen, it's 0 kilojoules per mole, right? The standard free energy of formation of a pure element in its standard state is 0 by definition. And then for diatomic sulfur, it's 79.7 kilojoules per mole, right? So you might be looking, oh, sulfur is a pure element. Why isn't it 0? Well, because Diatomic sulfur is not the standard state of sulfur because remember, in order for it to be considered a standard state, it has to be in its most stable form. Diatomic sulfur is not the most stable form of sulfur. And so we have a positive value of the standard free energy of formation. Diatomic sulfur does not form spontaneously on its own. Okay, so now we are in a position where we can calculate the standard Gibbs free energy change for the reaction, which is equal to, and again, this isn't the answer, this is just what's going to help us find the answer. What we're really trying to find is K, right? But in order to do that, we need to know what all the other variables are, right? So again, it's going to be the sum of the standard free energies of formation of the products multiplied by their coefficients minus the sum of the standard free energies of formation of the reactants multiplied by their coefficients. And so if you look at the products, right, so the coefficient for the hydrogen is 2, but if you look at its standard free energy of formation, it's 0, so we can ignore that. The other product is the sulfur. The coefficient in front of that sulfur is 1, and then it's 79.7 kilojoules per mole. So that's the products. Then we're going to subtract from that the product of the coefficient in front of that H2S times the standard free energy of formation of H2S, which is minus 33.4 kilojoules per mole, right? So I'm going to go ahead and calculate that real quick. So we have 79.7 minus 2 times negative 33.4. And I get a value of delta G standard for this reaction is equal to positive 146.5. Let me try that again. All over the place here. Positive 146.5 kilojoules per mole, right? So it's a positive value, which indicates that the forward reaction in which 2 moles of H2S become H2 and S2 is non-spontaneous. The reverse reaction, where hydrogen and diatomic sulfur come together to form H2S, the reverse reaction, that's the spontaneous one under standard conditions, right? So let me erase everything that I no longer need. So I don't need this table anymore. I don't need this calculation stuff, but we do need our standard delta G. That's why we calculated it. So I'll just go ahead and put that off to the side over there. And so now at this point, what I'd like to do is I'd like to just algebraically isolate my K value, right? So if I do that, what am I gonna do first? Well, again, I'm trying to solve for K, right? So what I'm gonna do is I'm gonna isolate the natural log of K term all on its own. And so I'll get that the natural log of K is equal to the following. So basically what I'm doing here is I'm dividing both sides of this equation by minus RT, right? And so I get natural log of K equals minus standard delta G for the reaction over RT, right? I think so. So we have natural log of K, but we don't want natural log of K. We just want K, right? So how do we get rid of this pesky natural logarithm? And the answer is, if you want to get rid of a natural logarithm, what you need to do is you need to raise e to the power of both sides of the equation. So e, that's Euler's number. That's the sort of the base of the natural logarithm. So every logarithm has a base to it. The base of the natural logarithm is e. So what we're going to do is we're going to raise e. Let me do this in a different color here. So we're going to raise e to the power of both sides of this reaction. And that gets rid of that natural log, and you end up with just K, right? And so what you end up with is K is equal to E, Euler's number, raised to the power of this entire expression where we have negative delta G standard for the reaction divided by RT. right? And if you have a fancy schmancy scientific calculator like mine, it's really not that fancy. It's only like $30 on Amazon, as I mentioned previously. You can type that entire expression into your calculator fairly easily, right? So at this point, I think we could just go ahead and use this formula, just plug our numbers in, and that solves the problem, right? So what we're going to do is, again, we're going to take the Euler's number E, and we're going to raise it to this whole thing here, right? So we're going to have negative delta G standard for this reaction, and it's in kilojoules per mole. But one thing I'm going to do is I'm actually going to convert this into joules per mole, and I think it'll be abundantly clear as to why I do that. So if it's kilojoules, if it's 146.5 kilojoules per mole, then it's going to be what? It's going to be 146,500, right? 1, 2, 3. Yeah, 14. So 146,500 joules per mole, right? That is my delta G value in joules per mole. Please, if anybody's watching, please double check to make sure I did that conversion correctly. One of my previous episodes, I did like one of these conversions in my head. I got it wrong, and it was a huge embarrassment. Okay, so then in the denominator of this, we have RT, right? So R, that is, you know what? I'm going to turn these parentheses into brackets just so I can make sure I'm doing this clearly here. So do the square bracket. Okay, so R, what is that? That's 8.314, and that's joules per mole per Kelvin. That's the gas constant. That's just something that I would highly recommend you commit to memory. And now we can see it's clear why I converted the delta G value to joules. It's because our R is in joules, right? So that kind of makes sense. All right, and then we are going to multiply it by the temperature, which is 25 degrees Celsius, which of course, when converted into kelvins, becomes 298 kelvins, right? Yeah, because all you need to do to get from degrees Celsius to Kelvin is add 273. And so we can see here that all of our units are going to cancel out, right? Joules cancel, moles cancel, kelvins cancel, and we're left with a unitless number, which makes sense because equilibrium constants don't have units. They are unitless, right? And so at this point, it's just a matter of using that calculator, plug this in there. Somewhere on your scientific calculator, there should be an E to the X button. So that's the button on your calculator that you're going to use to raise E to the power of this entire expression here. So bear with me while I do that. So we have E to the negative 146,500 divided by 8.314 times 298. I think I have this. Yeah, I think I did that correctly. Okay. And the value that I got for the equilibrium constant is a very, very small number. A very, very small number. I got a value of, let's see if I can just shrink this down a little bit just so I can have, whoops, didn't mean to do that. Just so I can have a little bit more room here. The value that I got for the equilibrium constant, K, is equal to 2.1 times 10 to the negative 26. That is a very, very small number. Now, it kind of makes sense that the equilibrium constant is small, right? Because remember, the forward reaction is spontaneous, is non-spontaneous, right? And so it would make sense that since the forward reaction is non-spontaneous, that the equilibrium would lie more on the reactant side of the equation, where you have like a reactant favored equilibrium. In other words, the concentrations of the reactants at equilibrium is high compared to the products, which translates directly into a very, very small value of the equilibrium constant. So these are kind of things that I like to think about when I'm doing problems. It's like, you look at your answer and you're like, does it make sense conceptually? Right? Does it actually accord with the scientific principles that we're talking about. And you can see through my reasoning here that yes, it does. So, all right, everybody, that's going to do it. So let me, I always forget to turn the music off when I'm doing the intro, but that is going to do it. That is thermodynamics all wrapped up. I thought, doing these practice problems would be a good way to wrap up this topic. The other aspect of it too is that I wanted to buy myself some more time to choose the next topic to talk about in my live stream. I still haven't really landed on a topic that I want to cover after this. So anybody who has any feedback at all, whatever you want to see discussed on this channel, what topic do you want to see? Do you want to talk about like electrochemistry or radioactive and nuclear chemistry? Or do you want me to just pivot and talk about organic chemistry? Those are all highly likely possibilities. I just would like to get some direction. Maybe I'll put up a poll on my YouTube community page to see kind of where you guys are at, what topics you want me to cover. So yeah, any feedback you guys want to give, I would highly appreciate it. I sincerely hope that these practice problems have been a valuable exercise for you. And I am going to get going. I'm pretty tired. It's been a pretty long live stream. So I love you guys very much. And I will see you in the next live stream series. Take care.